off the screen there a little bit. Advanced technology here, sponge. Okay. Let's see. Next one. This is a pretty easy one. All right. How does the gravitational force vary between two masses if the distance is doubled? How does the electrostatic force between two charged particles how does that vary if the distance is doubled? And explain both equations and physical applications. So basically, you've got two forces. You've got force gravitational and force electric. Okay, and they both depend on the inverse of the distance squared. Okay, just things that you need to know. Okay, so F grav, that is equal to G, universal gravitational constant, times m1, m2 over r squared, and F electric is equal to K times the charge, Q1 charge Q2 over r squared, little charges. So knowing these two formulas here, they look very similar, don't they? I mean, the only thing different is the gravitational constants, the electrical constants, and instead of masses, use little q's. Okay, so which I think is like the mini mass or something like that of the electrons. Okay, so if the distance is doubled, the force between two masses of the charged particle is going to be 1/4 the original. So basically, you can show that in either case, if r is doubled, if you put 2r for r in those, you have g m1, m2 over 2r squared, and here you have k q1, q2 over 2r squared. Okay, so just square those out, you have g m1, m2 over 4r squared. You have k q1, q2 over 4r squared. So you can see the 4 there. You always just take that out. That's a fourth. That's a fourth. So it's going to the force is going to be a fourth. It would be a fourth of the original. That's what happens when you square the radius, is the distance there. So so hopefully that helps you see that, because they're inversely proportional to the square of the distances between the masses. If you double that distance, and to explain it in practical purposes, I mean, if you've got, let's say, some charged particle here, a charged particle here, if you double that distance, obviously it's going to be that gravitational force between the two is going to go down, and it's going to go down by, it's going to be a fourth. It's going to be a fourth of what it originally was. Just like if you have two magnets, and the two magnets are kind of pulling together. Well, if you pull them apart even just a little bit, that force is way down. But when they're really close, there's a lot of force there. So pretty simple. You just need to know your equations for gravity and for electricity, and that's basically it. And these are charged particles, not charges. So just so you know. All right. Next, this is just a classic problem where you're dropping something off or kicking something off the top of a monument. So we all do that all the time. Just kidding. Okay. So given the following diagram, calculate the distance traveled by the ball being thrown off the monument. You guys want to draw your diagram? That's my monument. Okay. And they're saying this is 555 feet. Okay, and a ball at the top, and I'm definitely not an artist, so just so you know. Alright, so V0 is equal to 50 feet per second, and basically we just want to find the distance. Okay, it's a classic problem. Basically, main things you want to do, just break it into its components. We're basically going to be solving for dx. We already know dy. Just use your formulas. You're going to solve for time and plug that back into the other one. So real quick, dx, this here, the distance x, is going to be equal to velocity in the x direction times time. Okay? Distance is equal to velocity times time. Okay? Distance equal rate times time. You've probably heard it as that before. Okay, so dy is equal to v0y, okay, plus 1/2 at. Okay, just a formula you need to know. These are common formulas used in physics. You've probably seen them before. The velocity in the y direction is 0. Okay, so you don't have to worry about that. So this is really equal to 1/2 the gravitational constant times t squared. Oops, sorry, squared. Okay, so in this case, we know the y is 555 feet. And normally, when you work these problems, you probably want to convert them to their standard standard forms. So instead of feet, you probably want to use meters, stuff like that. But these are going to cancel out anyway, so it doesn't really matter in this particular problem. So it's equal to 1/2, and it's either 9.8 meters per second squared or 32.2 feet per second. Times t squared. Okay, and basically you just set this up and solve it for t. Just do the calculations and you get 5.87 seconds. Okay, so now you know the time. Since the time is going to be the same, you kick it off either way. It's going to hit the ground in 5.87 seconds, but it's also going to travel this distance in 5.87 seconds. So you just plug it in. Per second times 5.87 seconds. That's equal to 293.5 feet. So the distance traveled in the x direction, just use your velocity times time, it's 293.5 feet. Okay. Next problem. Okay, next one, and this is going to be, this one's going to be